Right, for number one, it says an object is moving towards a motion detector. So I think of like towards as backwards as back towards something. So that would have a negative velocity. And it tells me it has a positive acceleration. So if your velocity and your acceleration are in opposite directions, that means they're working against each other. So that means it would be slowing down because the velocity and acceleration are opposite directions, opposite signs. If this had been towards with a negative acceleration, then it would have been speeding up, but it was opposite, so slowing down. We have two tables, and I have position as a function of time for two different carts. One is going to move at a constant velocity, the other one is at a constant acceleration, and we're trying to decide which. So I'm going to look at the distance traveled in each interval. If this is at 15 meters and then 0.5 seconds later it's at 15.375, it's moved 0.375. And then from 15.375 up to 16, now it's moved 1.125. So this is not moving the same distance each time. So let's look at this one. It was at 15, now it's at 20, it moved 5. 20, now it's 25, it moved another 5. So this one is moving exactly 5 meters in each 2-second interval. So this one is the one at a constant velocity because it travels the same displacement each time interval. Whereas this one is increasing the distance it travels each half second. So this one was a acceleration. And it says for the cart with a constant velocity, we want to find the velocity of the cart at 2 seconds. So you can go to 2 and you can use this. Or you can think the velocity is going to be constant, so you actually can use any of these. And because it's constant velocity, we use our constant velocity equation, displacement over time. Now the trick here is if you use 2 seconds, totally fine, but 20 is not my delta x. Delta x is the displacement, so that would be from 15 to 20, we said it was 5 meters. So the displacement is 5 meters in 2 seconds, which gives me a velocity of 2.5. What it would look like if you used another point, that would be fine. If you use the last point from 15 to 35, or yeah, 15 to 35, it would have gone 20 meters in 8 seconds. So then that still gives me a velocity of 2.5 because it's constant. So this is your answer. Just make sure you are not plugging in position for delta x. Delta x is how much that position has changed, the displacement. If I have been given the position of an object with an equation that looks like this looks super similar to my x naught plus v naught plus 1/2 at squared equation. So that means that the x naught is like this constant right here. The v naught t, oops, I didn't put t. V naught t is like the 15t term. And then the 1/2 at squared term is like the 10t squared. So for x naught, that's easy. It's just 4, so the initial position is 4. For initial velocity, that's easy, 15t v naught t, so 15 would be your v naught. Acceleration is a little bit trickier, because I have 1/2 at squared and 10t squared. So that means the 10 is not my acceleration, because 10 is 1/2 of the acceleration, so my acceleration has to be 20. And then you can always double check. Plug in 20, 1/2 of 20t squared would leave me with just 10t squared. The instantaneous velocity at 5 seconds. So I want to know my velocity after 5 seconds. Well, v naught is 15, acceleration is 20, x naught is 4. I want to find after 5 seconds, to find the velocity after 5 seconds. You can use v is v naught plus at. V naught we said was 15, acceleration of 20, and 5 seconds. Now you just plug this in and you get that your velocity after is 115. And that's at least reasonable because I start with some velocity and I'm accelerating, so it should be with a positive acceleration and positive velocity, so it should be getting faster. And the instantaneous acceleration at 5 seconds, well, my acceleration isn't going to change. We said that it was 20 meters per second squared, it's still 20 meters per second squared. The velocity will be changing because there's an acceleration, but this is constant acceleration. And the motion of the object after 5 seconds, well, if your velocity is 115 and your acceleration is 20, that's a positive velocity and a positive acceleration, so it's moving in the positive direction. And because they are both the same sign, that means it is speeding up, b. For number 4, we have a cart that is rolling on a ramp with a motion detector at the bottom. Would the velocity be positive or negative? So here the velocity is going away from the motion detector, so that's positive. So I have a positive velocity. The acceleration is towards the motion detector, so that's a negative acceleration. And is the object slowing down or speeding up? Well, if I have positive velocity and negative acceleration, those are opposite signs, so it's going to slow down. And then I want to sketch the velocity versus time and the acceleration versus time graph. Acceleration is easy because I have a negative acceleration, so it'll look like this. My velocity, I start with a positive velocity, but I know that it's going to slow down and until it goes to 0, so I have put positive velocity slowing down. Similar, I'm trying to sketch the velocity versus time graph, but now the velocity and the acceleration are both towards the motion detector. So that means I have a negative velocity and a negative acceleration, which means it's going to be speeding up. So negative velocity means it has to be on this part of the graph, the negative part. It can't be positive at all. And negative acceleration means it's going down. So it looks something like this. So even though this is going down, this is still speeding up. It's just speeding up in the negative direction. Alright, so we have a velocity versus time, and we want to know when it passes through the initial position. So that means displacement you want to be 0. So you want the area under the graph to cancel out to be 0. So if you look, the first part of the graph, so all of this section right here is going in the negative direction because you have negative velocities. And you can calculate, I have a base of 4, height of negative 4 divided by 2 because it's a triangle, so that gives me negative 8 meters. So at 4 seconds, I've gone backwards 8 meters, so I can't be at the initial position. At 2 seconds, I've gone back 4, so that doesn't make sense. Displacement would be negative 4 here, and then displacement would be negative 8 here. So I want displacement to be 0. So then let's look at 5. So I'm going to use a different color because now this part is going forward. If I look at 5, I can do the math, but I also can look, like this area is definitely not enough to cancel out this area. So let's look at 6. And that looks a lot more reasonable because 7 would be like a lot more, right? Way too big. It would be end up forward where it started. So let's try 6, and then my base would be 2. My height would be 8 divided by 2. I would get positive 8. Negative 8, positive 8 cancel out, so displacement would be 0 at 6 seconds. 5 is not enough. 8 would be too far forward. The interval, it moves the greatest distance. So from 0 to 1 second, that would be this distance. From 1 to 2 seconds, that would be this distance. From 2 to 3, that would be this distance. I'm running out of colors. From 5 to 6, that would be this distance. And then from 6 to 7, that would be this distance, this area under the curve. Well, the greatest area under the curve is this pink section, 6 to 7. And 6 to 7 should make sense because it's going at a faster velocity in here. They're all for 1 second, so if I go at a faster velocity, in that 1 second, I travel farther. And 7 is asking to rate the magnitude of the acceleration. So magnitude means you don't care about sign. So you don't care if it's positive or negative. Don't care if positive or negative, just like the bigger acceleration. And I have from 0 to 2, 2 to 4, and 4 to 7. So you can actually just go and calculate the acceleration. So this goes from 0 to 4 meters per second in 2 seconds. So the acceleration in the first part would be negative 2. And then here it's the same acceleration, it's just positive 2. So A is positive 2. And then here it goes from 0 up to 12 in 3 seconds. So then this one has an acceleration of 4. Now, because it says magnitude, I don't care about the sign. So the acceleration in the last section was faster or bigger than these two, which were equal to each other. So then your answer is B. 4 to 7, this last section has a bigger acceleration, and then these two have an equal acceleration from this one to this one. 8, we have a cart, negligible friction. an initial velocity up the ramp, the cart rises a distance, turns around, and travels back, so it's going up, and then it stops and turns around and comes back the other way. And we want to know the sign of the displacement, velocity, and acceleration the moments at the highest point. So up here, so if you think about, that is between going up and going down, which means the velocity would be 0, the same way your y velocity is 0 for a projectile between going up and down. So you can cross off C and D. Your acceleration is back towards the motion detector. So if it is towards, that is a negative acceleration. So that means A, 0 velocity and negative acceleration. And the reason we have a positive displacement is because it is some positive distance away from the motion detector at the top. Number 9, we are sketching position graph, velocity graph, and acceleration graph for a cart placed on a ramp as shown. So at the beginning, your V naught is 0. So that's easy for velocity graph. At the beginning, V naught is 0. And it's going to be going down, so I'm going to have some negative velocity. And because it is low friction and at an angle, this is going to accelerate down. And then when it hits this point, now it doesn't accelerate anymore because it's not at an angle, but it's low friction, so it shouldn't slow down much either. This one we can say would be at a constant velocity. So I'm going to start with my velocity graph. I have no velocity at the beginning and it accelerates down, so that means it would be getting faster in the down, in the negative direction. And then it goes to a constant velocity, so it speeds up to some speed and then it stays there. So it would look like this. It would be going down and then staying flat. And then your acceleration, I do have some acceleration here, and then at constant velocity, your acceleration would be back to 0. So something like this. And then these at least match, right? Negative, this is going down, 0, it stays flat, so that's good. Position graph's a little bit harder, so I know that at the end, I want it going down at or that doesn't have to be down, but it's moving at a constant velocity. And so I want to show that the position starts slow, so like flat, and then it gets steeper because it's speeding up, so it would look something like this, and then it's going at a constant velocity, so that part would be straight. It's changing speed, it has an acceleration here, and then it's just straight. Here, so we have a velocity versus time graph. I said that there was a starting velocity, V naught does not equal 0. So I'm going to make that a positive velocity going up, and then I know it's going to slow down on its way up, so I start with some positive velocity and then it slows down. And you could continue, it doesn't necessarily tell me like go until it hits the top, or you might have it go hit the top and then turn around and come down, in which case it would just continue like this. It doesn't really matter as long as you at least get the first part. Now the third graph, so we have some starting velocity 0, and it's going, you can say like down and to the left, so I'm going to make this negative velocity, and it's increasing in velocity here, so there's some acceleration, and then it would be constant velocity here, because it's not tilted, it wouldn't accelerate. And then up here, it's going to change speed. It should be slowing down here because it's going up again. So I'm going to start with some velocity going down because it's accelerating in the negative direction, then it stays at a constant velocity, and then it slows down back to 0. So this would look like this, or this would be the velocity graph for this situation. All right, matching the position versus time and velocity versus time to the situation described. So if it is moving forward with a constant velocity, that's easy. That's graph 3. Moving forward is going up. Constant velocity is straight. And then if it's constant velocity, your velocity graph must be constant, and it would be positive and flat. So that would be E as the velocity versus time. Moving backwards at a constant velocity. So again, I want my position graph is straight. It just needs to be going down. So that's graph 5. And then constant velocity, it's just negative, would be B. Moving forward and speeding up. Moving forward means it's going up, so it's either 1 or 4. And then speeding up means getting faster, so it should be getting steeper. That's graph 1, because it's getting steeper as it goes. It starts flat and becomes steeper. And then the velocity graph would be going up, because I'm increasing the velocity. It's forward, so it's positive, so that is graph F. Positive velocity, and then it's getting faster. Moving backwards and speeding up, so the only ones moving backwards are 2 and 6. If it's getting faster, I want it to be getting steeper, so that means this is graph 2. And then if it's moving backwards, I have negative velocities, and I want it to start slow and get faster, so that's A. Next one, moving forward and slowing down. So the only one left moving forward is graph 4, and I know it's slowing down because it gets flatter, so graph 4 makes sense. If it's moving forward, I have a positive velocity, it's just decreasing. So C starts with some positive velocity and goes to a rest or ends at 0. And then moving forward and slowing down, so all that's left is 6, or sorry, moving backwards and slowing down. So this one is moving backwards because it's going down, and I start fast and I flatten out, which is slowing down. So go backward to slow down. And going backwards means I have to have a negative velocity. Slowing down means that it's going back to v equals 0, so I start with some negative velocity and it slows to 0, so that one was D. 12, we want a velocity versus time graph for a car that moves at constant velocity. So I can automatically cross off B, because that would be increasing velocity. I want it to move with a constant velocity and then slow to a stop, so velocity would be 0. So these both check out. I have some constant velocity and then it goes to 0, constant velocity and then it goes to 0. And without pause, it moves in the opposite direction. If it's going in the opposite direction, that means if it was positive, now it's negative. So the answer would then be A, because I have constant velocity, slows to 0, slows to a stop, and then it continues that same acceleration, that same slope, and in the negative velocity direction. 13, which segment does the cart move the greatest distance? So this is a velocity versus time graph, so the distance would be the area under the curve. So A to B, B to C, C to D, and then lastly D to E. Definitely the green part, so A to B would move the farthest because it has the greatest area under the curve for its section. C and D would probably be the least, well maybe these two would be the least. This would be the second greatest, A to B is for sure the greatest without doing any of the numbers. We have distance versus time, so the fact that it's measured in meters, that's like a position versus time graph, and we were matching the situation. A says a child runs at a constant speed for 40 seconds before stopping. So I actually have two that go at a constant speed and then stop, so we'll come back to that one. A panda moves slowly at a constant speed before stopping, so that is the same situation, it's just the panda is slower. This one is less steep, so that would be the slow panda, and this would be the child running and then stopping. Cheetah stalks his prey, moving slowly, stopping occasionally. That's going to be this one right here, because it moves and then stops, moves and then stops, moves and then stops. And a rabbit runs away from a farmer, not stopping for anything, that's constant velocity forward, D. 15, the driver of a car going at 20 meters per second makes an emergency stop by slamming on the car's brakes and skidding to a stop. How far would the car have skidded if it had been traveling at 40 meters per second? So two ways to do this. If your V0 is 20 and then it goes to 40, that means you have twice the initial velocity, and you're wondering how that's going to affect the delta x. So I looked at an equation that had V0 and delta x in it, and that's the last equation. V squared equals V0 squared plus 2a delta x. I want to know how the delta x would be affected if I put a 2 V0 in. So let's think this would have to be 0 because it goes to a stop. So if I instead have 2 V0 squared, well, this is getting squared, so that would become 2 V0 squared. So then, 2 squared is 4. So it become 4 times as much for the delta x. So it was a 4 times as far. Now for some of you, that doesn't make as much sense. That's totally fine. What you can do is make up numbers. So you could say, okay, V0 is 20. It goes to stop, V is 0. Make up some acceleration. Say it's 10. Find delta x with this. So it would be 0 squared is 20 squared plus 2, acceleration of 10 delta x. So then just go to your calculator, find delta x for an acceleration of 10. And then you get delta x is 20. Now do the same thing, but now with a velocity of 40. So 0 squared is 40 squared, same acceleration. What would your delta x be? 40 squared, divide the 20 over. Now my delta x would be 80. So if it's going from 20 over to 80, see how that's 4 times the distance, 4 times as far, A. Either way works, whatever makes the most sense to you. 16, a ball is kicked at 14 degrees at an angle of 20. How high does it reach in the air? So 14 meters per second at 20 degrees. First thing you want to do is break it up into the x and y. So Vx is 14 cosine of 20, and Vy will be the 14 sine of 20. And make sure your calculator is in degree mode. 14 cosine 20, 14 sine 20. So I get my x velocity is 13.16, and then my y initial velocity is 4.79. And then your acceleration is negative 9.8, and your y velocity goes to 0 at the top, which is perfect because I'm looking for how high it reaches that y displacement at the top. So you could use the v equals v naught plus at, find t up, and then plug into your delta y as v naught t plus 1/2 at squared. Or you can just use the last equation, v squared is v naught squared plus 2a delta y. Doesn't matter, you get the same answer. Square, 0 squared, make sure you're using your y initial velocity because you broke it up into x and y for a reason. And now you can just rearrange and you would get that your delta y is 1.167. And again, you could plug into the first equation, get t up, and then just plug into the second equation with the t up. You should get the exact same answer. Alright, now we have velocity versus time graphs, and we are again matching description. Now they are velocity versus time graphs. So, for A, it says the car accelerates, and then it stays in the same speed, and then accelerates some more, and then gets to another speed and stays there. So I want one that's going up, staying there, increasing velocity and staying there. So that is going to be this graph right here. And then let's just double check. It accelerates, stays the same speed, accelerates, stays there, slows down, stays there, and then speeds up again. So A. B, I want a car that is accelerating forward until it reaches a nice speed for a couple seconds, then slams on the brake and switches into reverse. So again, accelerating forward, stay there, and then slows down and going into reverse. So that's this one right here, because I'm increasing in speed, staying in the speed, slowing down to 0, and then as soon as you go negative, that's the backwards direction or in reverse. This one would be B. It starts off moving fast and gradually slows to a stop and gradually speeds up into reverse. So I start with some velocity, goes to a stop, V is 0, and then it goes into reverse, so that would be the negative velocity. So this is C. Car stuck at a red light, your velocity would have to be 0, and then speeds up, goes the speed limit, stays the same speed, and then slows down to a stop. So this one was D. A snail is moving along in a straight line. Its initial position is -5, is moving away from the origin, so that's the positive velocity. And then slowing down means opposite sign of the velocity, which means negative acceleration. And it told me x naught was negative, so I should have negative, positive, negative. So your answer is D. Negative position at the beginning, positive initial velocity because it's moving away, and then negative acceleration because these two have to be opposite if it's slowing down. 19, if you throw a small ball upward, you throw it again at twice the speed, which correctly describes the change. So if I throw a small ball upward, and now I do it but twice the speed, so it should take more time in the air, and it should also go farther. The acceleration should not change. So your acceleration is -9.8. Throwing it up faster doesn't make gravity stronger or less, so that doesn't make sense. So then you can also cross off D. A says that the ball travels twice as far, and C says that it spends twice as much time in the air. Well, we said that it would take more time and it would go up farther. We just don't know whether it's twice as much time or twice as far. So let's look at our equations. So we want to know how 2v naught would affect the delta y and how it would affect the t. So the first equation would be the v is v naught plus at. That's how the v naught would affect the time. And how the v naught would affect the delta x, or delta y in this case, could be the v squared, v naught squared plus 2a delta x. So then let's think. This is a linear relationship. I do something to v naught, that changes the t by that same factor, whereas delta y and v naught squared, well, this has a squared, so there's going to be some squared I have to take care of. Well, if this is a linear relationship, twice the initial velocity would mean twice the time, so it was c. This one, if I have twice the initial velocity, it gets squared, so it would actually be 4 times the distance, which is very similar. I think it's actually the exact same as number 15 that we just did. Right, I've got a position equation. So let's first identify what this all is. This is like your x naught plus v naught t plus 1/2 at squared. So then the 4 right here is not my a, that's the 1/2 a. So then your acceleration is 8. The 5 is your initial velocity, the v naught t, negative 5t, and then 4 is my initial position. At the beginning is the object slowing down or speeding up. So let's look. I have a negative velocity and a positive acceleration at the beginning, so that would mean that it is slowing down. The instantaneous velocity at 3 seconds, so I'll just plug in, v is v naught plus at, v naught is negative 5, acceleration is 8 after 3 seconds. Negative 5 plus 24, that gives me 19 meters per second? Yes. So that would be my velocity after 3 seconds. Instantaneous acceleration at 2, well, the acceleration isn't going to change, it's 8 meters per second squared. And at 3 seconds, I now have a positive velocity and positive acceleration, so it should be speeding up. So the first part, when your a and your velocity were different directions, it slowed down, and then it started going in the positive direction. Now they're the same sign, so now it's speeding up. A ball is thrown with a speed of 10 meters per second at some angle. Sketch the velocity and the acceleration for the horizontal and vertical components. So horizontal is easy because your your x velocity is constant and there is no x acceleration. Your y acceleration is easy, it's negative 9.8. Let's go ahead and write constant velocity. So now you just have to think about your velocity for the vertical component. Well, it starts going up because the y velocity goes to 0 at the top and then it ends negative. So it looks something like this. Start positive, go to 0, and negative. Here we have a position versus time graph. And we want to know which of these two answers are correct. So first I would look, they're both straight, so they're both constant velocity. C is steeper, so C is faster because it's steeper. And then D is a little bit ahead of the C at the start, so D has a head start. And at some point, D has his head start, but he goes slower, so C will pass him. So at 10 seconds, C and D have the same velocity. No, that is not true. They're just at the same position. That's not the same thing. They have different steepnesses, which is velocity for the position graph. At 10, D is passing C. Nope. C is the one that is passing D because before it was behind, and then after that time, it is now in front, so no. C is moving with a constant velocity, yes. D is moving with a constant velocity, yes. Faster than C, no, D is slower, so that's not true. And it says two answers, so that means D and E. But we can talk about why. So D starts with a head start compared to C. Yes, it has some initial position at the beginning, whereas C does not, so D has a head start. And at 10 seconds, the two are in the same position. Yep, they are meeting, and that means that their x's are the same, their position is the same, not their velocity. Sketching the velocity versus time graph for C and D, well, they're both constant velocity, it's just that D is slower. So this would be C, and D would be a constant velocity, just a little bit lower because it's slower. Here we have a velocity versus time graph. So car X staying at the same velocity, so constant velocity. Car Y is not at a constant velocity. It goes from 0 velocity, so that means it starts from rest. And it accelerates forward. So it's getting faster as it moves forward, getting faster and faster and faster. At 20 seconds, it's asking, is car Y behind? Is car Y passing? Is car Y in front? Or does X have an acceleration greater than Y? Well, let's look. Car X would have no acceleration, and car Y would have an acceleration, so it has some positive acceleration because it's increasing velocity. This is constant, no acceleration. So x does not have a greater acceleration than y. It has none. Car y is in front, car y is passing, or car y is behind. So a lot of people are tempted to say passing, but what's meaning right here is actually their velocity. So they're only coming to the same velocity right there. And car X has been traveling at that velocity for a while, whereas car Y started from rest and only just got up to that speed. So car Y is going to be behind car X because it's been going slower this whole time and only just caught up to this speed. Or you can think about it, the area under the graph. After 2 seconds, car Y would have this area under the graph, whereas car X would have twice that area under the graph. Either way, totally fine which way you want to explain it. And assuming both cars start at the same position, what time does car Y pass car X? So that would be when their area under the graph is equal. So that's going to be at the very end, because in that case, now see how this, wow, that's not working. This pink rectangle would be equaled out with this green triangle. So at the very end at t is 40 seconds, because now it's gotten even faster, which makes up for the point where it was slower than car X at the beginning. And the acceleration versus time for X and Y, well, car X, we said, has no acceleration, and car Y has some constant positive acceleration. Constant because it's just straight, positive because it's going up. So that would be your answer.